Today, this is for class 11 physics, system of particles and rotational motion. So, in your textbook, it starts from system of particles and then it moves to the rigid body. It starts from system of particles and it moves to the rigid body. I'm not going to explain the whole chapter, but I'm going to deal with the important points here because this is an important chapter and I'm going to deal with the most basic and the important points here. So first of all, they started with center of mass and system of particles. So at first they considered a system of two particles and they found out the location of the center of mass, and it comes out to be x is equal to m1 x1 plus m2 x2 by m1 plus m2, which is given in your book. Then they extended it to two-dimensional system considering three particles. So here your coordinates x1, y1, x2, y2 and x3, y3 comes here. Next they extended it to three dimension, and again they converted all this into this three dimensional into position vectors. So they the location of the center of mass, they describe it in the form of position vector. So that means they confine the whole three formulas in x, y, z into a single formula. Now here again they, for system of particles, that is capital M into capital A, that is equal to F1 plus F2 plus F3 plus dot 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 Fn, because it consists of n number of particles, and F1 F2 they are the forces on the respective particles, where capital A is the center of is the acceleration of the center of mass of the system of particles. M is the total mass of the system of particles, and here F1 and F2 they are the forces acting on the individual particles, and this F1 or F2 or F3 they are the sum of the internal forces and the external forces. Here the sum of the internal forces is 0, so only the external force remains here. So capital M into A, that is equal to F external, and A is the acceleration of the center of mass of the system of particles, and F external it's x on the center of mass. So that means center of mass, I have not told you about center of mass. Center of mass, it is the where the whole mass, a point where the whole mass of the body is concentrated, where the whole mass of the body is concentrated. So here, and again they have also shown that the rate of change of momentum is equal to the F external. So they have proved that the Newton's second law is also applicable to the system of particles. Now, they have moved to the rigid body. What is a rigid body? A rigid body is one whose constituent particles retains their relative position even when they move under the action of an external force. They retain their position. Their position, the constituent particles of the body does not change. It remains where it is. It remains where it is. That is, if the body undergoes displacement, that every particles of the rigid body will have the same displacement. And if the body rotates through a certain angle, every particles rotates to the same angle about the axis of rotation. Now, here comes the there are but I'm going to start with the torque, because torque, which is also called as the moment of the force, the force or torque in linear motion, force and torque, but torque is not analogous to force in linear motion, but force, it is very important because because of force there is work done, and because of work done there is power consumed. So I have selected torque because torque Because of torque, there is work done. And the most important point here, the force, it creates two effects. One is the linear motion, and other it gives a turning effect. And because of the turning effect, the rotations takes place. So here, the torque. So they here torque, that means here you see that this is y and this is x axis. Now let this be the position vector. Here a particle p is here, and the force acting here is F. Say, let us take this F. Force acting here is F, and this force is making an angle theta with this position vector, this x, y, z. So here your torque, that is equal to R cross F. So according to your maths, it is a cross product. So the direction of the cross product will be perpendicular to the plane containing these two vectors. That means these two vectors are in, let us consider that they are in xy plane. So your torque will be along the z axis. So your torque will be along the z axis. And torque, what is torque? Torque, it is this moment of a force. Torque, it is moment of a force. And remember that moment, for a moment of a force, here, this see, and here this is the force, this is the fixed point, this is your arm, and the force, it acts perpendicular to its moment of a force. This is the fixed point, and this is your arm, and this is the force acting on it, which is perpendicular to the arm. So now you see how they have done this. How they have done this, you see. We know that here, we know that torque. What is torque? We know that torque, we let us take the torque, that is equal to, where this magnitude of this, that is rf sine theta, rf sine theta. Now, and proceed here, so that it makes angle 90 degree with this is your origin, it makes 90 degree with this. So here this is theta, so this is theta, and this is 90, so this will be 90 degree minus theta. So this this is the component of r vector. Here you see this is the component of r vector, that is r cos 90 degree minus alpha. This is alpha, not theta. This is the component. This is r cos 90 degree minus theta. This is your r cos 90 degree minus theta. This is your component. This is your component of r vector. This is the component of r vector. This is the component of r vector. R vector along this direction. So here you see that torque, it F r sine theta dot F. So what is r sine theta? This is equal to r sine theta. This is r sine theta. So here this is the r sine theta. So here you see that r sine theta, it is perpendicular to F. This r sine theta is perpendicular to F. So your torque is equal to r perpendicular F. So here you see this r sine theta is perpendicular to F. So the same case here, it has been automatically, it has been satisfied. So when you are calculating magnitude torque, that means it will be r perpendicular to F, and this is also moment of the force. Here you see this is the fixed point, this is the arm, and this is the force, it makes a 90 degree. So here you see the same effect has been brought here by the help of this maths. Here the same effect, that means torque is equal to r perpendicular F, or it can be torque that is equal to r dot F perpendicular. It can be r dot F perpendicular. So see how beautifully they have formed it. And when you are, for maths calculation, when you are doing the calculation, you have, that means you have to take r perpendicular dot F, r perpendicular F. or R into F perpendicular. So this both things they have satisfied here. This is the main interesting point here in case of Turk. And why I have selected Turk? Because Turk, it because of Turk there is work done, and when there is work done, that means you there is a power calculation. That means there is energy. So here in rotational motion, torque plays a major role. Like in linear motion, torque plays a major role. So here you see that torque that is equal to Rf, that means torque is equal force Newton meter, and here you see work done. Work done is equal to Newton meter. They have the same unit, same dimension. So we can say that torque is analog to work done of the linear motion. It is analog, we can say. Now, means torque ultimately what is it? It is the measure of turning effect of the force. It is the measure of turning effect of force. Turning effect, that means here the turning effect, that turning effect is called the force. Torque. Now, some directions you can consider here, some directions here, that is um, you can consider, that is here you have seen that when I have drawn it, you have seen that this is y, this is x, and here you have seen that this position vector is in outward direction, and your force is also in outward direction. So if the force is in opposite direction and the position vector is in opposite direction, then also your cross product will give the same direction. But if your force is in opposite direction and your position vector is in the outward direction, then the torque will be minus z. Then the torque will be minus z. But if this force is in opposite direction and this position vector is opposite, then your cross product, it will be have the same direction as earlier, that is r cross f, as earlier means in this direction. So you must remember that direction is also very necessary while explaining it. So here this r position in outward direction, this force is also in outward direction. So this is very important. Now here you see that the torque, it means as force, means uh, in linear motion there is work done because of force. So in rotational motion, because of torque, there is also work done. So here you see work done. Now work done, how to calculate this work done? Work done. This is xy. Our body is rotating like this. So here, uh, this is the P1 point and this is R1, and the force acting here, this is uh, F1, and with R1, this is position vector. These all are vectors. That means I have to show arrow. I have to show arrow. This, it is making an angle alpha 1, and after time delta t, this is, it is making an angle theta. So after time delta t, it has moved, this P1 has moved to P1 dash point. Now the angular displacement is, this angular displacement is d theta, this angular displacement is d theta, and here this is the ds1, this is the displacement, and its direction is given by the, by tangentially, by the tangent, its direction is given by the tangent. and force and ds1 is making an angle of say phi 1. Now here you will see that what is work done? Work done, that is equal to F1 dot ds1. This is your work done. Now you have learned in your earlier classes, that is if this is theta and if this is r and if this is the arc length, so theta is equal to L by r, so r theta will be equal to L. So here, that means here this will be your ds1 arc length, ds1 will be equal to r1 d theta. This will be r1 d theta. So now work done that is equal to f1 ds1 dot product cos angle between the uh, ds1 and f is phi 1, so this is phi 1. Now here you see that this tangent tangent is perpendicular to the radius. Tangent is perpendicular to the radius. So here your phi 1 plus alpha 1 will be 90 degree. So now here work done, that will be equal to F1. What is ds1? That is r1 d theta. And what is your cos phi 1 phi? That is equal to cos 90 degree minus alpha 1. So now here work done, that is equal to F1 r1 d theta sine alpha. So you know that your R1 F1 sine alpha is torque. So your work done is equal to torque d theta. So here you have easily found the value, the formula, that is work done. Work done by this force in rotating it by d theta. Work done by this force in rotating it by d theta is equal to work done torque into dot d theta. Now, you can make other formulas from here. So other formulas will be, you can easily make other formulas from here. You can make other formulas from here. That is, you take dw, work done by delta t. That means from here to here, delta t, it has shifted from P1 to P1 dash. So this will be torque d theta by dt. That means let me divide it by dt. Uh, let us take this as dw. This will be more better because ds1 for small displacement we have considered dw. For small displacement we have considered dw. So this is dw for small displacement. So here this will be dw is equal to torque d theta. So this will be better if we consider dw by dt. So this is equal to power. So power is equal to torque, and this is angular. This is angular velocity. This is angular velocity here. This is angular velocity. Now from here again, you can see another formulas can be derived from here. You will see you can derive another formulas, that is you know that kinetic energy is equal to half I moment of inertia, uh, not I moment of inertia into omega square. So your this is kinetic energy, that is equal to half a moment of inertia into omega square. So this kinetic energy means work done. If you differentiate it, that is I. If you with respect to dt, it will be 2 omega d omega by dt. So this will be I omega d omega by dt is angular acceleration. So kinetic energy, if you differentiate kinetic energy with respect to time, this will be power. So this will be power. So this W is equal to I omega alpha. So omega cancels out. So your torque will be is equal to I alpha. So your torque will be equal to I alpha, means moment of inertia dot alpha. So therefore I have selected torque, means from torque you get energy, and from work done, and from work done you get power. So it plays an important role. Now, and most interesting thing, uh, it has been explained in your book. A most interesting thing, that is the most interesting thing is that your angular velocity is a vector quantity. It has angular velocity is a vector quantity, and mm, when a for a rotating body about a fixed axis, for a rotating body about a fixed axis, the angular velocity vector lies along the axis of the rotation. That means for a rotating body, it is if it is rotating body, your angular vector, that means your uh, uh, angular velocity vector is along the axis of rotation. It is along the axis of the rotation. It is along the axis of the rotation. This is a very important thing. It has been told in your book, that is angular velocity, it is a vector, and for rotation about a fixed axis the angular velocity lies along the axis of rotation and points out in the direction in which the right hand thumb screw rule would advance. Thumb screw rule would advance. That means the thumb screw rule will advance along the jet means along the axis of the rotation. Your thumb screw will advance. That means your thumb screw, that means thumb, will advance along the axis of rotation. So here it has, this is an important point. That means your angular velocity lies. That means your angular velocity is along the axis of rotation. Now, because it has told that it is your angular velocity, it is a vector component, so omega cross r, here omega cross r. So here you see that your omega, it has, it is along z axis, your omega is along z axis, and let us take like this, rotating in a circular path. So here your omega is along z axis, and r, this is your r, this is your r. So your omega is along the z axis, and this is your r vector, that is a position vector. This is the axis about which the body is rotating. It is the axis about which the body is rotating. So omega cross r. So this vector must be, so this vector must be perpendicular. This must be perpendicular, uh, must be perpendicular. This vector must be perpendicular to omega and r. So that will be the tangent here. So this will be the tangent here. So this tangent is the direction of omega cross r. That means the vector omega cross r is perpendicular to omega and r, and therefore it will be the tangent to the circle. The tangent to the circle will be the direction of this omega cross r, and this is satisfied by, and this the same condition is satisfied by, that means here this condition is satisfied by your velocity, this condition is satisfied by your linear velocity, so it is equal to omega cross r. So it is satisfied by your uh, This condition is satisfied by your linear velocity. So V is equal to omega cross R. Omega cross R. This is an important point they have told here in your book. And one more thing it has told here, that is the in omega cross R, your magnitude in omega cross R, that is, first of all, let me explain more, let me see some, let me explain here. Let me, actually it is, this is, and this is a particle, here it is rotating here. We have taken the origin here O, and this is the particle P here, and this is Z. So omega is along Z axis, and this is your R. This is your R vector, and this is your perpendicular component, that is R perpendicular. This is the, this vector, it is R perpendicular, it is the component of R vector. So this is the actual figure, this is the actual figure, this is the actual figure. Your particle is moving in a circular path, and this is your origin, and this is the position vector of this particle, and your omega is along the z axis. Your omega is along the z axis. So omega cross R. So your tangent to the circle will be the direction of. This is the direction of omega cross R. The tangent to the circle, tangent to the circle is the direction of, the tangent to the circle is the direction of omega cross R. And the most important thing it has been explained here, that is the, this omega cross R. See here, this is the actual figure. This is your z axis, this is your origin, this is the axis of rotation. Here p particles is rotating in a circular path, and this is the origin. So the position vector of the p particle is here r, and uh, this omega cross r, here you see omega cross r, and the direction of omega cross r is tangent to the circle, is the direction of omega cross, tangent to the circle is the direction of omega cross r. Now the magnitude omega cross r, so it's what is its magnitude? Your magnitude is omega r perpendicular, this omega into r perpendicular. This is the magnitude, this is your magnitude, this is your magnitude, and the direction, this is the direction, tangent to the circle, tangent to the circle, tangent to the circle, tangent to the circle is your direction, is your direction. This condition is also satisfied by V. So V is equal to omega cross R. This is the actual explanation. This is the actual explanation. So this is an important point. It has been told here in your book. And if the particle is along the x-axis, so your R will be 0. If the particle is along the x-axis, your R will be 0. That means the velocity will be 0. The particles on the x-axis, the velocity of the particles on the x-axis is 0. And each particle of the body moves in a circle which lies in a plane perpendicular to the axis and has the center of its axis. This is an important line. This is an important line. That means this is an important line. Why this is an important line? Let me explain it. That is, if this is a suppose rigid body, if this is a rigid body, if this is a point P, so this point P will rotate like this, perpendicular. It rotates in a circle which lies in a plane perpendicular to the axis. If the point P is some other particle, it will rotate like this, perpendicular to the, this is perpendicular to the plane. This is the perpendicular in a plane perpendicular to the axis and has its center on the axis and has its center on the axis. This particle will move like this, perpendicular to the axis in the plane perpendicular to the axis. This is an important point. Now, an important line has been told here. Rotational motion does not apply to a particle. Only the condition for translation equilibrium apply to a particle. Rotational motion, that is, rotational motion is not applied. Rotational motion is not applied to a single particle. Why? Why? Because a particle is a point and it has no mass, size, or shape. Therefore, we cannot apply a force to it in a way such that it could cause it to turn or spin. The concept of torque is meaningless for a single particle. But the condition of translation equilibrium is applicable because the force acting on the particles must be transitional equilibrium. That is, the force acting on the particles must be zero. This is a very important line. It has which has been told in your textbook. Now, the another important point here is that uh, when a rigid body is in equilibrium, when is the rigid body is in equilibrium, means a rigid body is equilibrium when the linear momentum and the angular momentum both are constant. When your linear momentum as well as your angular momentum both are constant, then we say that the rigid body is in mechanical equilibrium. Both your linear momentum and your angular momentum must be zero. So your angular momentum, that is r cos p is the linear momentum. This is your angular. Both must be constant. Both must be constant. So now comes here the next important point is the moment of inertia. For linear motion, here there is mass. Now for rotational motion of a rigid body, for a rotational motion, what is analog to mass? What is analog to mass? And that is moment of inertia, and that is I is equal to mr square. I is equal to mr square. That is the moment of inertia. It is analog to the it is analog to your uh, uh, mass in rotational motion, and this moment of inertia, that is equal to I is equal to mr square. Now here you see that the most important point, as mass of a body resists a change in the state of linear motion. As mass of a body, it resists a change in its linear motion. It is the measure of inertia of linear motion. Similarly, moment of inertia about a given axis of rotation resists the change in its rotational motion. It is a measure of rotational inertia of the body. Means moment of inertia, it is the rotational inertia of the body. It resists about moment of inertia about a given axis of rotation resists a change in its rotational moment of inertia. It resists a change in rotational motion. Similarly, mass of a body, it resists the change in the state of linear motion. So mass is a measure of inertia of linear motion, and moment of inertia is the measure of rotational inertia of the body. So the what is the use of it? The use of it is that you have find that the flywheel, it, its moment of inertia is very large, and this flywheel resists the sudden increase or decrease of the speed. Means it act this moment of inertia, it resists. So it is the it resists any change, moment of inertia. So its moment of inertia uh, is very large, so that it can resist the sudden increase or decrease of the speed of the vehicle, and it keeps the speed of the vehicle uniform. It keeps the speed of the vehicle uniform. So these are the important points which are given in your system of particles and rotational and rotational motion. Thank you.